Oh, students, Stride here again. Today we start Chapter 12 notes. Chapter 12, titled Forces in Motion, Section 1. We deal just some basic types of forces. Here illustrated a man pushing against the wind and an umbrella, and that push from the wind is called a force. So wind can be a force. One of our key questions: how do forces affect the motion of an object? And a force can cause a resting object to move. It can accelerate a moving object by changing the object's speed or direction. And the definition of a force: a push or a pull acting on an object. So if you remember that idea of a push or a pull, that's pretty simple, good definition for a force. When we measure force, we can use a spring scale, illustrated here in a grocery store. And when we use a spring scale, we measure weight, which is a type of a force. Our units for force is the Newton. In this definition, a force that causes a 1 kilogram mass to accelerated weight of 1 meter per second And when we write it out, it's kilogram dot meters per second squared. When we represent force, we can use arrows. Force is another vector. So vector, remember, we'll always have a direction with it. We can use arrows as illustrated here to illustrate that direction. The size of the arrow illustrates the magnitude. There are the lengths of the arrows, show the relative amount of force or its magnitude. And the way they're pointing is direction. Here, the force is going down. And when we talk of weight, it is always a force going down. So, another key question: how do forces affect the motion of an object? When the force on an object are balanced, the net force is 0, and there's no change in an object's motion. When we have unbalanced forces, the object is going to accelerate. And by balanced forces, we mean forces that are going to cancel each other out. They may be equal forces going in opposite direction. May have two people pushing on something, each end, equal force. The object's not going to go anywhere. So, use a term we call the net force, overall force acting on an object after all forces are combined. Forces are going in the same direction, we add; opposite direction, we subtract. Balanced forces give us a net force of 0. Balanced forces, net force of 0. Very key little idea. We can have many forces. It states here an unlimited number of forces, giving us a net force of 0. Here's the illustration. Two teams on a tug of war. If they're pulling with equal forces, opposite direction, or net force is 0, and there'll be no change in motion of that rope. Unbalanced forces happen when the net force is not equal to 0. And unbalanced forces will always cause an acceleration, as we stated earlier. So forces can add or subtract from one another, same direction, we're going to add them together. Opposite directions, we're going to subtract. And these will be two types we will deal with in this course. Now, they can be going perpendicular or some other idea. Then we get to work with the Pythagorean theorem or something. We'll leave that for a later time, a later course. So if they're going this way, what we have to do is we would sketch a little rectangle, and the net force is the diagonal of that rectangle. If they're equal and opposite, the net force of 0, balanced forces. Another type of force, friction. And we have 4 main types of friction. You'll need to know what these are. And our 4 main types of friction are static friction, sliding friction, rolling friction, and fluid friction. Friction, a force that opposes motion of an object that touch as they move past each other. So the objects have to be touching, they have to be moving, or they'll be moving or trying to move past each other or along each other. And what's preventing the motion is friction. Static friction deals with objects that are not moving. Static friction always acts in the opposite direction of the applied force. If we have some type of a ramp and an object sitting on that ramp and it's not moving, that means there's static friction preventing it from moving because that object has a force trying to make it go down. So if it's not moving, there's an equal force of friction pushing back up on it. Those two cancel each other out. Sliding friction opposes direction of motion as it slides over the surface. Sliding friction will always be less than static friction. So, the example I had on the preceding slide, if we make that ramp a little bit steeper, that thing's going to start to try to move down the ramp. And as it's sliding down, it's got its force of weight going down, and it has a little static friction trying to make it go slower. Another example of static friction and sliding friction, static friction. If somebody's pushing on this potted plant, that would be this arrow, and the potted plant does not move, that means there is a force of friction pushing back on it. So that would be our friction force. Yeah, sliding friction, if we push on it a little harder, it's going to start to move. And as it's sliding across the floor, we're applying a force to it. And there's a force of static friction slowing it down a little bit. And we see here we have motion. Rolling friction, another type of friction, acts on rolling objects. Rolling friction tends to be much, much smaller than either static or sliding friction, usually in the neighborhood of 100 to 1,000 times less. That's why we put wheels under things. It makes them easier to move. There's less friction between the wheels and the whatever surface we're on than the object itself and the surface. So with rolling friction, much less, makes it easier to move. Well, ball bearings. In here, ball bearings in the wheels themselves make it easier to turn the wheels, less friction than sliding friction. So, put ball bearings in many things, or other types of bearings in engines, and lots of different things to make less friction. Fluid friction, another main type of friction, an object is moving through the fluid. The more common kinds of fluid friction is air resistance. Air resistance, if an object falls through the air, got resistance from the air pushing back up on that object. Air resistance. Also get fluid friction if something's moving through the water. So fluid friction increases with the speed of the object as it moves through the fluid. So as an object is falling from a very high height, initially there will be very little air resistance and it picks up speed greatly. But as it keeps falling, the air resistance increases, causing it to speed up at a smaller rate. And eventually that object will reach what we call a terminal velocity, where the air resistance balances out the acceleration due to gravity. Gravity, another kind of force. In what direction does gravity act? Gravity acts downward towards the center of the earth. So it's more than just downward, towards the center of the earth. And how do gravity and air resistance affect the falling object? This is what I mentioned a little bit ago. Gravity causes objects to accelerate downward. Air resistance acts in direction opposite to the motion and reduces the acceleration. And again, the farther the object falls, the greater the air resistance becomes. Gravity is a force that acts between any two masses. So any two masses have a gravitational attraction for each other. It's an attractive force. It can act over large distances. Here's an example of balanced forces. You got force of gravity here, pulling down on that great big rock. But as it's not moving, there's balanced forces, and there's a supporting force moving up. Both gravity and air resistance affect the motion of a falling object. As the objects fall to the ground, they accelerate and gain speed. And here's that term I used a little bit ago, terminal velocity. It reaches a constant velocity or speed. Falling object when the air resistance balances out the force of gravity. Here's an animal, a flying squirrel. Doesn't really fly, but it glides. And it takes advantage of air resistance. So, using air resistance to slow its fall. Projectiles. Projectile motion follows a curved path. So, combination of initial forward velocity and downward vertical force of gravity causes an object to follow a curved path. One of our key points. By a projectile, we just mean some falling object. So projectile motion of a falling object, that's the projectile, after it's given an initial forward velocity. This is what we did when we did that little lab activity a few days ago. We rolled a ball off the desk. We gave it a forward motion, then it went out and it curved down. And air resistance and gravity, only forces acting on a projectile, and that thrown object, that projectile, will always follow a curved path. Masses, again, do not make any difference on falling objects. They're going to fall at the same rate. Doesn't matter. Here, illustration of the green and the blue at this falling at the same rate, hit the ground at the same time, as long as we can ignore air resistance. And if they got one falling straight down, one curving out, so straight down or curving out, again they're going to hit the ground at the same time, as long as there's no significant air resistance, because the only thing making them go down is gravity. A few quick review questions. Objects at rest, which of the following statements must be true? Yeah, I'll try to answer these questions. Write down whatever you want to help you in your notes, and try to answer them. Then look at our correct answer. So, object at rest, which of the following statements must be true? Indeed, the net force is 0. If unbalanced forces, it'll always be accelerating, which means we have movement. So objects at rest, if it's at rest, it cannot have unbalanced forces. And we have no cases where there's absolutely no friction. That's impossible. And we will have no cases where there's no forces acting on an object, because for sure we always have gravity. But the net force is going to be 0. Which the following is not a type of friction? Yeah. If you miss these, make sure you listen to my explanation. If you got it right, you can kind of skip on through my explanation. Yeah, there is no pole friction. We have static, sliding, fluid friction, but no pole friction. The other type was rolling friction. Gravitational force act, what direction? And that's just part of our definition, downward towards the center of the earth. Ball thrown in the air follows a projectile course due to the initial velocity and so makes projectile motion, that initial velocity and the force of gravity. Air resistance will alter the projectile path, but will not cause it to curve. Motion of the earth has nothing to do with it, and the mass of the ball will not affect the curved path. Mass of the ball can affect the air resistance, causing the path to alter a little bit, but it'll still be curved. And the SI unit of force is 1 kilogram meter per second squared, also called 1 Kepler, and that is false. It is called 1 Newton. This part was true, but this part was false. It's a Newton. That's section 12.1 notes. Again, write down everything you need, read the textbook, add any other additional things that you think would be helpful to you. Remember, you can use your notes on the quiz I'll give you later. And that's all for now.